Okay, let's dive right into this. I want you to picture the absolute most terrifying, invincible force in the universe. We're talking about a literal cosmic monster acting like the ultimate vacuum cleaner, capable of devouring whole planets, entire stars, and yeah, even other monsters just like it. These gravitational titans warp the very fabric of reality so intensely that absolutely nothing, not even light itself, is supposed to escape their grasp. So today in this explainer, we're going to decode the mysterious hidden life of black holes.
You know what's really wild? Theoretical physicist Jan Levin points out something totally fascinating. Even Albert Einstein, the actual guy whose theories paved the way for their existence, didn't really think nature would allow such a crazy object to exist, right? For the longest time, there were just these baffling, theoretical oddities on a chalkboard. But here is the massive plot twist of our story today. To truly understand these impossibly enormous, universe-breaking giants, we actually have to use the physics of the absolutely microscopic. We literally have to look to the quantum realm.
Section 1. Hunting the Cosmic Monster. How we found the mythical beast.
So before we can even begin to break down a black hole with quantum physics, we really need to understand how they went from being just, purely mathematical myths into terrifying observable realities. Our chronological journey actually kicks off in December of 1970. NASA launched a rocket off the coast of Kenya carrying this small satellite named Uhuru, which translates to freedom in Swahili. Now, Uhuru is the very first space telescope dedicated entirely to observing X-rays, which are these high-energy light waves normally blocked by our atmosphere. And, well, by 1971, buried deep in Uhuru's data, scientists spotted something deeply ominous hanging out in the constellation Cygnus. That was it, our first real evidence of a black hole. Fast forward just a few years to 1974, and Stephen Hawking makes this massive theoretical breakthrough about their true nature. Then jump all the way to 2015, and we finally detected their completely invisible collisions.
But to truly appreciate what we're actually dealing with here, try to wrap your mind around this number, 10 billion. We know now that black holes aren't actually all that rare, and honestly, some of them are genuinely monstrous. Supermassive black holes sit right at the center of most large galaxies, and yep, that includes our very own Milky Way. Some of these absolute behemoths contain up to 10 billion times the mass of our own sun. 10 billion. They are the ultimate destroyers. I mean, we don't even have the laws of physics to actually predict what would happen to us if we actually fell inside one.
Section 2. The Quantum Achilles Heel. The universe's biggest monster meets the smallest physics.
For the longest time, the story kind of just stopped right at the event horizon. But it turns out, these seemingly invincible cosmic giants actually have a fatal weakness. Just imagine the stark contrast here. On the one hand, we've got the classical clockwork view of physics, where a black hole is just a one-way trip to oblivion. Once you pass its event horizon, nothing, absolutely nothing, ever gets out. But on the other hand, we have this totally shocking quantum view, first proposed by Stephen Hawking back in 1974. He theorized that something actually did escape from these mighty giants, radiation. He essentially argued that the most massive, powerful objects in the entire cosmos are actually susceptible to the physics of the absolutely tiniest scales.
Okay, so to understand how anything could possibly escape a black hole, we have to completely rethink empty space itself. Theoretical physicist Clifford Johnson puts it perfectly right here. Empty space itself is not empty. It's seething with possibility. In the totally bizarre reality of quantum mechanics, a vacuum isn't just a boring, empty void. It's more like a bubbling, chaotic soup where a particle and its antiparticle are just constantly popping into existence out of nowhere, dancing around for a split second, and then instantly annihilating each other right back into nothingness. And crazy enough, this is happening everywhere all the time.
Now, I want you to really lean in for a second and think about this. Imagine this constant, microscopic quantum dance happening right on the razor's edge of a black hole's event horizon. You know, that supposed one-way door. What on earth happens when a particle and an antiparticle just pop into existence, but one of them gets sucked into the black hole right before they can annihilate each other?
Well, this brings us to a seriously mind-bending concept known as Hawking radiation. When one of those partner particles falls past the point of no return into the black hole, the other one is suddenly left stranded without a partner to annihilate with. So it literally just flies off into space. To someone watching from far away, it looks exactly like the black hole is spitting out radiation. And here's the crazy part. Because the black hole is emitting this energy without necessarily eating any new matter to replace it, it means the mighty black hole is actually shrinking. Given a very, very long time, we're talking way longer than the current age of the universe, these invincible monsters will actually evaporate and completely disappear, utterly vanquished by the quantum world.
Section 3.
Listening to space-time, hearing the monster in the dark.
So we talked about how quantum mechanics slowly, eventually destroys black holes. But how do we actually observe these invisible monsters interacting with each other out there in the pitch black of space? Well, this brings us to gravitational waves, which are essentially tiny little ripples in the fabric of space-time itself. Back in the early 20th century, Einstein merged space and time into this one single concept, space-time, and he theorized that mass actually warps this fabric, which is exactly what we feel as gravity. But this came with a pretty startling implication. If really massive objects accelerate, they should create actual ripples that spread outward at the speed of light. Now, funnily enough, Einstein himself actually doubted this at first. He thought these ripples would just be way too incredibly small for humanity to ever actually detect.
To prove Einstein's lingering doubts wrong, scientists actually had to rely on quantum technology. The LIGO observatory basically acts as this giant ultra-sensitive quantum sensor using incredibly stable lasers. And here's roughly how it all works. Step 1. A perfectly pure, ultra-stable infrared laser is split in half and sent down two arms that are literally 2.5 miles long, positioned at perfect right angles to each other. Step 2. Mirrors at the very ends of those arms reflect the light right back. Because they're perfectly out of phase, they completely cancel each other out, meaning zero light is actually detected. But step 3 is where the magic really happens. If a gravitational wave comes washing through the Earth, it literally stretches and squeezes space-time itself. One arm gets slightly longer, the other gets slightly shorter. The lasers don't cancel perfectly anymore, and a tiny bit of light leaks out and hits our detectors. We're literally measuring a change in distance that is smaller than a microscopic fraction of a single atom. It's wild.
And this absolutely incredible setup led to a monumental breakthrough back in 2015. LIGO actually detected a signal. It was the catastrophic collision of two black holes spiraling violently into each other. As Janna Levin so vividly describes it, all of that power came out in the ringing of the drum of spacetime. I mean, in that fleeting fraction of a single second, more power radiated from the collision of those two black holes than was generated by literally all the stars in the entire universe combined.
Seriously, let that sink in for a second. The 2015 LIGO detection was the single most powerful event recorded since the Big Bang itself. It wasn't just some random blip on a computer monitor somewhere. No, it was a monumental explosion that temporarily warped the literal fabric of reality all across the cosmos. And the crazy thing is, we only caught it because we used the ultra-precise quantum physics of a laser to measure the unimaginably small stretching of a 2.5-mile tunnel right here on Earth.
As the experts pointed out, this was the most direct observation of black holes that we've ever had. A total, complete revolution in science. And it's just this stunning irony, right? The absolutely only way we can observe and comprehend the universe's most massive, destructive, and deeply mysterious entities is by mastering the fundamental quantum behaviors of light and atoms. The tools of the microscopic realm turned out to be the literal keys we needed to unlock the universe's most massive secrets.
Which really leaves us with this final, incredibly provocative thought. As researchers just keep refining this quantum technology, making these lasers more and more stable every single year, our ability to sense the microscopic stretching of reality is only going to increase. We're going to be able to see further out into the universe and way deeper into the subatomic realm. So what hidden cosmic monsters are we going to uncover next? The quantum age is honestly just beginning, and it feels like the universe is finally speaking our language.